record, and yeah. Turn that off. Right. So.
Okay. We'll start, right?
Yeah.
My name is Zhang. I'm a PETSc developer since 1999, so I'm the older one. There's another Zhang in PETSc team now. He's much younger, and he works on time stepping method. So I mainly work on the numerical linear algebra. Actually, everything, right? Depends on whatever needed. So today I will talk about PETSc DMNetwork, also the using MPI shared memory for vector scatter. Those are the recent additions to PETSc library. And you know PETSc library is a research package, so we constantly adding new features, new functionalities, and to address new challenges from the application. So what my goal here is to introduce you this new, very cool stuff, particular DMNetwork. I talked about this last year, and now I will talk again, but with a kind of more updates because we add more stuff to it. For example, like a network or networks. So my hope is some of you get interested and see your application can actually make use of this, because the interaction between the users and our developer is the driving force of the library. So it's very important. So this is not fully mature yet, but try to use it and then send us the request, and then we'll kind of further develop it. It's very, very cool stuff. I really like it myself. So let me see. Yeah. Okay, first let's start with the PETSc DM. This morning, Matt talked a little bit about DM. So according to Barry, the DM stands for data management. Is any way I can see? Yeah, it's abstraction for data topology and discretization in algebraic solvers. So most of you start using DM, mainly use the DMDA, which implements the structured meshes, right? And I talked about this morning. And then Matt wrote this called the DMPlex, which implements the unstructured meshes for PDEs. So what's a DMNetwork? DMNetwork actually is a subclass of DMPlex, which implements the simulation on the network, for example, like a power grid, water distribution, gas network, all those things. And there are more stuff for the DM. Actually, we can call the objects for the DM, or maybe the subclass of the DM. For example, like a DM forest, DM worm, I don't know some of those stuff. So DM telescope. Remember, PETSc is one word called extensible, right? So you always can add new things to it. Whenever there's a need for application, we add new features. So today I'll talk about DMNetwork, which is a recent addition to the PETSc. So DMNetwork is virtually is a new, we can call it a new object or new class in the PETSc library. It's a subclass of DMPlex and provide a specific abstraction for multiphysics and PDE-based network application. So 3 keywords for DMNetwork is for the multiphysics. I'll show you the motivation application. And then it's a PDE-based because there are so many packages dealing with the network. We deal with the network, but we are not working on like a manipulation of the network. We are solving multiphysics. And then it's PDE-based. Also, is the multiphysics built on the network. So originally, it's a couple years ago, the DMNetwork was developed by actually called Shri. He originally was in my class. So he's the electrical engineer and motivated by simulating the electrical grid. So you can see that graph. There's a generator, there's transmission lines, and also load systems. Traditionally, engineers will work simulating one system and then send the solution to the next one, like a transmission line, and then get the solution, then send to that. So that's the traditional way of the simulation of the multiphysics. And now with the arising of like a powerful machine and also the software, we want to solve all of them together, right, as a coupled systems. And so that's the motivation application. We have been working on that, and then our next kind of application is like this complicated, the surface water, underground water, and then the filtering of the water. So it's a water system. It's a network, PDE-based multiphysics. That's what the DMNetwork, this new addition to the PETSc is for. Right. So we all know that the scientific computing is moving from interpretive simulation toward predictive science, right? And previously, the traditional way of solving individual subsystems is no longer sufficient to simulating the multiphysics. So we want to do them as a couple, actually, the overall ecosystems. And that will tell us much more about it. And also, we know the simulation is not just for simulation to explain the physical phenomena. It's to help us to make a decision. For example, I made the electrical engineers, and the reason they want to do simulation is they want to use a simulation to help them design. For example, how much water needed for a power plant, and then how much resource we have. They run the simulation, and then they make a business or maybe engineering decision. So simulation is to make a decision, and that's what we want to do the multiphysics. Things are coupled together. So right now, so from the day I joined the PETSc team until now, I have seen how PETSc library has been progressive, right? In the beginning, it's 1D, 2D, three-dimensional simulation, and now it is the system-level simulations. So what's the system-level simulations? I got this from Wikipedia. So it explained it's a collection of techniques to simulate the behavior of large cycle physical systems, right? You can see the power grid, the water distribution system is like this kind of application. And then it's categorized by the involvement of multiphysics model. For example, like a power grid. When you simulate the generator, transmission line, and the load system, they are modeled by totally different mathematical systems, the PDE, right? And then you want to solve them together. So definitely one solver doesn't kind of answer all the system requirement. You have to use different solvers and then pull them together. So we need to have the multiphysics, the different solver for it. And it's cross-disciplinary. For example, when we work on coupled energy system, like the water, the power grid, the power simulation. And then the other system may be water distribution. So the people now, the electrical engineer may not know that much about water distribution. So then we have to have those people working together, and right now I keep getting that. And then PETSc hope to provide the infrastructure for the scientists on very different team working together. So we'll assume like the electrical engineering just write their function evaluation, the water experts just write their function evaluation in Jacobian, and then we provide the infrastructure for them to glue those things together and then provide the solver. So separate solver, the general assembled solver. That's the goal. So here is mainly the motivation is you're simulating the system as a whole can tell much more information, and particular help to make a decision, right, for design. So the DMNetwork is the objective for this class, for the DMNetwork, is to have a domain scientist. They can independently build their own model. And then we provide the infrastructure for them. So they can do their function evaluation, their Jacobian evaluation, and then the PETSc library help them to glue together. And you can see the example. We try to mimic this kind of behavior, the human activity to do the simulation. And then it handles the data topology and topology management for multiphysics, also PDE-based. So for example, like the power grid, the gas network, all those. And for DMNetwork, basically there are three building blocks, or three elements, we can call it. So one is the vertices, edges, right? They form the network, the graph. And then the third one is kind of new to this network. It's called component, because we want to do multiphysics. And the physics are encapsulated by the component. So component is like the physics, the PDEs, the number of variables, all those in the components, and then we put those components into the vertices, edges, and then build a whole network. And also it's built on the PETSc solver. So DMNetwork is designed to work with the PETSc solver because eventually you want to solve this. You want to split, you want to put them together, you want to do the hierarchical solvers, the linear solver, nonlinear, or time stepping. So it's developed with the PETSc solver. Here's an example. This is already in the PETSc library. So this is a simple example. It's a linear problem, electric circuit, right? So there are 4 nodes and 6 edges linked together. And then we have two actually simple equations. Actually, there are several equations. The equation for the node, the equation for the edges. So in this case, there are 2 physical components, and then user can build their own data structure. For example, branch is one. In this case, node is the other. The way to use DMNetwork actually takes those 4 steps. The first step is to build a graph, right? The edges, the vertices, and the connectivity. That's the first step. Right now, we do that in sequential. We have planned to implement that in the parallel. Once you have this graph, you add physics to it. So you add, for example, a power plant to a vertex. You may add a transmission line or a river into edge. That's the second step, add physics. So you have to register your components, and then you add the components. Also, you have to add the number of variables, right? How you are going to do discretization. The third step is partition, because we are going to simulate to run this in parallel machine. So the third step is how you do the partition over the multiple processors. We use external package like Prometheus or maybe Charcoal or something like that. Finally is solve. So it's a linear problem, it's a nonlinear problem, or time stepping method. So we use a PETSc parallel solver to do it. So those are the 4 steps using DMNetwork. So here is the previous example. So in this example, you see the first part is you read the user data. User have to provide the number of vertices, the number of edges, the connectivity for the graph. And then we create the object called the DMNetwork, right? You pass in the communicator because we are going to run in parallel. And then there are 2 physical components in this case, node and branch. That's the user data. So we register the components with the DMNetwork. And then you set aside. The set aside says the number of the subnetwork. In this case, only 1. This is a simple one. And the number of the coupled network. The coupled network we consider them as a separate because interface require a little bit different. In this case, it's 0 because I'm only handle 1 simple case. And then the number of local vertices, the local edges, and the global. That's very much like a PETSc matrices, right? And then the user provided the connectivity. That's called edgeless. And that's all. And then you just call setup. So this is the first step, setting the graph. So now we have a network graph. And then the next one is adding component, right? So add physics. And first we need to query each individual edges. And this is a very good thing I like about the DMNetwork. Overall, it's so complex, right? You have a networks, or you have a network on networks. And then by query, you only look at one edge, one vertex at a time. Once you look at one edge, it's a very simple thing. So you query the total range of the edges. And then for each edge, we add the branch. That's a physics, user physics, into it. And then you have to tell the PETSc library how many variables for that edge, right?
I have a question about that.
Yeah.
So, I'm assuming that the number of variables can have to match the components that we need, right?
Not necessary, not necessary. Yeah, component just physics. For example, it's a power plant, or in this case, it's just a branch. And then in this, for example, in this case, it's a very simple one. The branch is just one variable. For our water, I have to do DMDA there. And then depending on how long it is, and then what's my discretization, can be 100,000, yeah. So it's 2 different things.
Okay, because what I was wondering, how come the component that is assigned that doesn't tell it how many variables? Is there a situation where they
Now, component just a physics. It's an entity of the physics. It's like a power plant or it's a channel, water channel. And then how many variables? For example, this channel, the same component, right? This part, maybe there's 100 variables. Next part, maybe 1,000 variables. Yeah. Yeah, the component is a type. Yeah, so it's a different thing. You have to do it separately. Like our water pipe, one pipe can be short, and next pipe can be very long. So the number of variables is very different. Yeah.
Then would an edge be your rule for how two different nodes, like a power plant and a river or whatever, interact?
Yeah, well, that's a user can design. For example, this power plant, you put the power plant on the vertices,
Yes.
and then, so they may have like several edges up, and then you define those.
Sure.
So,
So a node would be like a domain specialist would give you everything you need for a node.
Yes, yeah.
And then somehow the edges are interdisciplinary, and that you have to know how two different
yeah, you
domains
can
interact.
incorporate that way. For example, the vertices are domains, right? The physics. And then the edges connect, like connectivity. But also you can put the physics on the edges. Like in our water pipe, we actually put the water, each water pipe into our edge. And then the vertex actually serve as a connection between two water pipes. So it's flexible. You can decide yourself. We just provide this graph, and then you put the physics under the graph, and then you define your connectivity. You can use edge as a connectivity. You can use vertex as a connecting. So in water pipe, we actually use the vertex. It's called a junction, connect two things together. Yeah, so it's very flexible. It's up to you. We just provide you logical graph, and then you put the real physics over it, right? So in this case, so for each one, once you have each edge, and then you assign the physics, you assign the number of variables. You do the same thing for the vertex in this case. And next, we do the partition, right? Do the parallel partition. And then do solve. For example, this case is a linear case. And then if you want to solve, you need the solution vector. And then once you pass in the DMNetwork, and then the PETSc library now how many variables, how large, how it's partitioned among all the process. So provide you the solution vector, and then you duplicate, get the right-hand side. Also, we provide you a matrix because you have the graph already, the connectivity, number of variables. But all those just the vectors and the matrices, the data structure, not the real thing. The real value the user has to provide is called form operator. That's the work the user has to do. I will show you. Once you have this, the rest is a standard. That's what the Matt told in the morning. You build the linear solver, and then you can play with different options, different pre-love method, preconditioner. So let me show you how to do the function evaluation. That's the user's subroutine. So in this case, form operator. In this case, we need to form the right-hand side vector. We need to form the matrix, right? What you are going to do? So the first thing is, for example, we are going to run over the network element. So I will get the range of the edges, and then I run the iterate over each edge. For each edge, first I query the physics, right? So now I build the branch over the edge. So I just query the branch, and then I got access to user application structure. So I got this data structure. Next, you need to find out where this, the index for the vector on the right-hand side or the solution vector. So you just query the offset, the variable offset. So that's all. You need the physics, you need the index, and then you just put your physics value into the vector, right? So this is, you have this whole network. User doesn't need to know how this vector actually is. You just query the physics, you query the index, and then you put your physics application value into that vector. That's for the right-hand side. You do the same thing for the matrix. So for the matrix, you query we have one edge. With one edge, you can query two vertices connect to it. And then you can query their index. So with the index for one vertex, the index for the other vertex, the index for the edge, and then you can build the matrix, right? Matrix is the connection of all those. And then you have a physical value put into the matrix, and then that's how you build your matrix, right? This is for edge. You do the same thing for the vertex. So this is how user provide their function evaluation. Basically, you run over all the edges, all the vertices. You query the physics, you query the number of actually the index for the variable, and then you assemble your stuff. And this linear case is same for the nonlinear problem. So DMNetwork is a class for representing PDE-based network. And it's very general and also flexible, right? So it's general, that means I already explained the vertices and the edges can be used to representing any kind of like the physics. Also can be used for the connectivity of those physics. It's easy to use, and you can see there through the query utility function, you can query a subnetwork, you can query a network pond, and also you can query a component, for example, like a branch node, I did over that example, a coupling element, you can do that. So over the DMNetwork, you can use the PETSc solver. So next, remember this is developed for using PETSc solver, and particular hierarchical composable solver. For the PETSc, there are 3 types of solvers very useful for DMNetwork. One is the domain decomposition. Domain decomposition is for the decomposition over multiple computing process, right? So for the DMNetwork, basically, you can have individual computer process to compute a subnetwork, right, put them together. And the field split. Field split is a decomposition of the physics. And you know we have a query function. You can query particular physics, and then very easy to get the index for the field split. So using field split with the DMNetwork is really, really convenient.
So can I ask, how would the field numbers get defined? So when you were doing it, you associated a component. Is that component a field?
Well, in this case, see, when you use a field split, there's one way to do it is you give the index.
Yeah.
Right? For example, I have a field 0, and then the field 0 have index this. So in this way, we can query the physics. For example, the branch. And then once I have a branch, I can query their offset. So then I can generate my all eyes.
Oh, so right now you're kind of making the split by hand.
Yeah,
Querying
right.
stuff.
Yeah, maybe that can be automated.
Right.
It can be written by, I think very likely we can support in the PETSc library. So right now you just query the same physics and then find their offset. And then you create this IS, and then that's all you need to do the field split. Yeah. Maybe you can do it in the library. So user can skip this step. Yeah, right now it's that step. And then you can use a hierarchical composable solver. For example, you put all those together. If you want to solve a subnetwork, you just query subnetwork, and then you apply some kind of solver to it. If you want to query a particular physics, and you query that physics, you apply field split. Different level, different hierarchy. So we did a prototype simulation called the water pipe, and I can show you that. So for this one, the first 2 equations describing single water pipe. Very pretty simple equations for the water pipe. And then the next 2 equations tells you the connection between the 2 water pipes. So in this case, actually, we use the edge to describe the water pipe. And then we use the vertex to describe the connection between the 2. Yeah. And for the initial solution, we solve steady-state problem. In this case, we found out the junction actually form a yield condition, the Jacobian. And then, so if we try to solve all of them together, it's really, really slow. Also, we have to use the LU direct solver, which is non-scalable. So we use the field split, get the junction out, and then apply the LU direct solver. Because junctions are small in our case. And once we have that, we apply like a block Jacobi LU for overall system and solve that very efficiently. And then we solve the time slipping method. So we run this on the as you see, for the using PETSc, all the solvers, we experiment until we find a set of solver really work well for our case. And then we put it in an option file, right? We don't have to change our program all the time. So in this case, we ran up to 30,000 cores per processor in a Cray machine. and then we simulate up to 2 billion variables. Most time until reaching very high core number, and then we got a pretty like a weak scalability. Yeah. So it shows this is robust, also accurate. Our next project is to couple the power system with the water system, right? So this is what we want to do next. And right now, we already kind of implemented the network or sub-networks. So this is an example in PETSc library, which is simulated. It's small, just for example. So there are two networks. One is called the power network. The other is water. And then show you how we put the two together. So the first, we read the data. And then so you create the DM network. And then in this case, I have total 3 sub-networks, actually 2 sub-networks. And then plus a coupling. So in this case, it will be different from the previous one. And then we set up the graph. And after set up graph, we have to query the sub-network. So this is the routine, you query sub-network. Once you get a sub-network, you can say the component for the power sub-network, the component for water, because they have very different physics components, and then the number of variables. Then we set up the graph, we do the parallel distribution, right? So this time is a network of the networks. And then we just do, so since we have 3 sub-networks, this time I created 3 SNAEs. This is a nonlinear problem, steady-state nonlinear problem. So I call this SNAEs power, SNAEs water, and then one for the overall SNAEs. Once you have all those, also we write individual function evaluation, and then we put them together. So this time when you do the solver, it's really convenient. I can run K1 iteration for power only. And then I pass the result for the next one because they use the same vector. And then I can run K2 iteration for water nonlinear solver. Then I can run K3 times for couple, right? So you have a flexibility how you solve those problems. And here's the example how you do the function evaluation. That's always the critical one. So in this case, we assume the power engineer know how to do their function evaluation. So we query the first sub-network, which I identified as 0. That's for power. And then we call the power function evaluation, written by electrical engineer. And then the second one, I query the water network. And then I will call the subroutine written by the water experts. And then finally, I will handle the coupling. So this is a coupling network. And then we will do some function evaluation over there. So this is a function evaluation routine. And yeah, that's also, once you do the function evaluation, also you can do the Jacobian. For example, in that example, already in the PETSc release, the power grid system has analytical Jacobian, but not the water. So actually you can make use of that to accelerate your computation. So next we want to do, actually currently we are working on this water, open channel water network. We want to read the real data. So this will be interesting application. We try to move to like a large data simulation, right? From computing centric and then to the data driven application. At the end, we want to do this one, the multiphysics. So the summary for the DMNetwork. So it's developed for multiphysics, PDE-based, and network application. It provides abstraction through simple abstraction and to define and query the components, the physics. And the application interface provides the ability to switch and compose different PETSc solvers. So you only write one program, and then you can experiment different solver, different combination, to find the optimal solution to your application. And simplify the programming, the parallel core. It's run on parallel machine, on very, very large parallel machine, right? 100,000 cores, you can do that. We already run a prototype water pipe that got good results. So I'm hoping this will get some of you interested. You may have an application and consider using this. And talk to us. I would like to see more application, and then we can push this object forward. That's all.
Any questions while we change over? There've been a bunch during the talk, I know.